Kafue River, one of the longest rivers in Zambia, stretching over 1,600 kilometers through exotic landscapes. The Kafue River is the largest tributary of the mighty Zambezi. Throughout its course, the river is a natural lifeline, supporting activities like fishing, transportation, irrigation, and most importantly, hydroelectric power generation.
When you look at the unique opportunity we have with the Kafue River, starting with the Teji Dam, which was constructed primarily as a holding reservoir for what we are now calling Kafue Upper, there's already an opportunity which was presented that you could actually install a power station at the Teji Dam itself. So apart from just holding the water, you could actually harness the resources there and be able to come up with a second power plant. Now, interestingly, just slightly further down from the current Kafue Upper, you could then still put up what we're calling the Kafue Gorge Lower. When you look at this arrangement, it's almost like a battery of stations, and we call it a cascaded arrangement. That is one of the strategies that we are engaging to make sure that we maximize the utilization of the resources that God has given us in this country.
Kafue Gorge Lower, once it comes on board, will be able to deliver into the system 750 megawatts of power. That is in terms of capacity, but in terms of energy, we expect that it will be, in the region beyond 2,500 gigawatt hours of energy. So that's the capacity we're expecting from Kafue Gorge Lower.
Our vision as ZESCO is to ensure that we become a hub for power trading by year 2025. This is our vision. And in order to achieve that vision, obviously you need power stations, you need interconnectors to our neighboring countries. Why do we want to be a hub? It's very simple, because we are endowed with 8 neighbors, so we have to take advantage. This is a very good situation in terms of having markets. So we will be developing more generation stations. We will be linking in terms of power, linking power to our neighboring countries through interconnectors, transmission lines, if you like. And therefore, in order to trade, we need to have more power, we need to have more interconnectors. And therefore, our flagship project of Kafue Gorge Lower is very, very key in this regard.
In the first episode of the Kafue Gorge Lower hydropower project, we looked at the overall undertaking, from its historic planning right through to its current execution. We interviewed various project managers and got a sense of what the project was all about and the benefit it will ultimately bestow on the people of Zambia. Here is a quick recap.
The Kafue Gorge Lower power project has been in consideration for quite a while now. The initial feasibility studies for the project were commenced in the mid-1970s by ZESCO, a company that was engaged to develop a second phase of the existing Kafue Gorge power plant. And they also extended to start feasibility studies for Kafue Gorge Lower. Since then, several other feasibility studies have been done between government and private partners, mainly with World Bank, that has looked to investing into the construction of the Kafue Gorge Loyola. The most recent one was through an MOU between government, Sino Hydro, and the KAD Fund, to where they looked at developing their project through an MOU.
After 2 years construction, the dam excavation is completed by this year, and the leveling concrete for the dam foundation is also done. We are almost ready for the RCC construction. And for the waterways, we completed the hydraulic tunnel. It's done already through. And the third shaft almost finished. The excavation almost finished. For the power tunnel, it's still under the construction, but we almost finished also. And for the powerhouse, the excavation is done, and now the concrete is under construction. So we can say the works is on track.
This project is divided into 2 phases. The first phase is what we call infrastructure works. They are enabling works. Under infrastructure, we have the road works, starting from the main road between Lusaka and Chirundu, and also the roads within site. We also have the administration building for Kafue Gorge Loyola Hydropower Development Corporation. We have the guest house that has to be constructed. We have the health center that has to be constructed. And we will have 157 houses for the staff that will be here, coming from Kafue Gorge Loyola Hydropower Development Corporation, as well as other stakeholders such as government workers, because we will have a school that will be run by government, a boarding secondary school. We are also going to have a primary school. We will have the sports center for recreation activities of the people that will be here during the operational phase. We are also going to have a police post just to ensure that there is law and order during the time. Then we have the main works. The main works, that's where the power will be generated. And the main works has various components which fall in categories of civil engineering, hydromechanical and electromechanical.
In this second episode, we'll take a more detailed look at each of its different components, why they are important, how they are constructed, and how they function. In the generation of hydroelectric power, water is collected or stored at a higher elevation in a reservoir, the dam, and it is led downward from the intake structure through the headrest tunnel, which then feeds the penstock at a lower elevation. The difference in these 2 elevations is known as the head. At the end of its passage down the pipes, the falling water causes turbines to rotate. The turbines in turn drive generators which convert the turbine's mechanical energy into electricity. Transformers are then used to convert the alternating voltage suitable for the generators to a higher voltage for long-distance transmission. The structure that houses the turbines and generators and into which the pipes or penstocks feed is called the powerhouse. The powerhouse has been under construction since the beginning of the project. This structure is the mother house for the generation equipment. It is special purpose constructed, as part of it will stand underwater. At the moment, the outside walls are complete and the structure is roofed. Only internal installation works are still being completed. The works on the dam wall are at an advanced stage, with the pouring of special concrete done round the clock. Immediately after the gates is the next vital intake structure known as the headrest tunnel and the penstock. This structure controls water flow. It is basically an enclosed pipe that begins at the water reservoir and terminates at the powerhouse, where it delivers the water that drives the turbines, which in turn generate electricity. At the KGL project, the headrest tunnel, which is excavated through the mountain, has been completed, and its walls are being steel lined. Let us now take a closer look at how the penstock is constructed.
This is the penstock installation workshop, where we are assembling the penstocks. Because of the size of the penstocks, they are coming in segments for transportation convenience. So what you see here, this is the steel lining, which will line the tunnels as you get to the turbine. Only the section towards the turbine is lined because of the high pressure in that section. The other sections of the waterway are concrete lined because the pressure is not as high as it is towards the turbine. The thickness of this is as high as 52 millimeters towards the machine.
The initial stage of the penstock construction starts with welding together 2-meter components. Once completed, additional stiffeners are added on the outside in order to increase overall stability. Next, the 2-meter components are further welded to make 6-meter segments.
So it's the 6-meter sections which are transported to the tunnel for installation.
The welding process of the penstock is done in 2 ways, manually and automatically.
What you see here is automatic welding taking place. Where we are coming from, we are using manual welding. So automatic welding is faster. If we had a way, we would have installed more of this equipment so that the welding is done automatically. the quality of weld that you get is better than the manual welding because you are relying on how good the welder is. But this is automatic. As long as your settings are okay, the weld you get is guaranteed. So on the equipment that you are seeing in here, there's a welding rod that's being fed automatically to the area that is being welded. And then there's some flux that is covering the weld. So depending on the thickness that is required, there's a number of welds that are done in order that you get to a stage where the inside of the penstock is not more than 2 millimeters. We are using 2 millimeters. The weld should not be more than 2 millimeters from this surface. So these penstocks are cylindrical in order to ensure that you maintain the shape, because you are connecting a 2-meter section to another 2-meter section. If one of the sections is oval, then it becomes very difficult to align them. So we have these supports that ensure that you maintain the shape of the penstock.
Once the welding is done, the inspectors carry out ultrasonic testing to ensure that the entire weld was done correctly. If the quality of the welding does not pass the test, it will be cut out and the welding redone.
These things will be embedded in concrete, and we do not want any leakages in the future, so we have to ensure that the weld is perfect.
Once this process is completed, the penstock components are painted.
This is a 6-meter section which has just come from the painting bay. If you can see here, there's a portion which is not painted. So this is how the surface was before it was painted. This was done in the sandblasting bay. This is where we clean the surface with some blast materials to remove any paint which is there. So this area has still been left because this section has to be connected to the next section. And so there's welding that is going to take place here. The thickness of the paint here is 0.5 millimeter. It's applied in 3 layers. You apply the first layer, give it time to dry. It's about 4 hours or so. Then the second and third layer. So it will be immersed in water. As long as the machine is running, machine is, has water in the penstock, this surface is exposed to water. In order to ensure that that water doesn't get to this surface and corrode this surface, we need to have this thickness so that the area is protected, the surface is protected from corrosion. You've seen the assembly of the penstocks at the penstock assembly workshop. So this is where those pieces are coming. So when they come in here, they are pushed, they enter on the other end, and then they are dragged on a trolley, which is moving on a rail, some rail line, which we've installed in here. Then they come in here and they are connected, so that we have one complete steel lining for the penstock. So there are joints in here. We have joints because we have to connect these sections together. Then once we've done the installation works, these supports need to be removed. So they have to be cut from where they are starting from and cleaned flush to ensure that the area is flush. We don't have any bumps on the surface of the penstock, because that will interfere with the flow of the water. So these have to be removed, and then you clean, just like we did at the workshop, clean the area and then repaint, because we don't want to have any areas that are not painted, because the painting is for corrosion protection.
the penstock and the sedge shaft work together to deliver a steady flow of water from the reservoir to the powerhouse, it is the turbines located at the end of the penstock that use this water flow to generate the actual electricity. In the case of KGL, there are 5 turbines, each with the capacity to generate 150 megawatts of electricity. This means that towards the end of its journey, the KGL penstock splits into 5 dedicated shafts. The equipment housed in the powerhouse comprises some of the heaviest components of the power plant. Up until now, tower cranes have been sufficient for all the lifting jobs. However, in order to complete the installation, heavy-duty overhead cranes are now required.
Today we are testing the overhead cranes, the powerhouse overhead cranes, 2 of them. Each one of them is a 200-ton crane. That's the main hoist. Then each one has an auxiliary hoist, which is 25 tons. So the 2 hoists have to be tested before they can be put to use.
Government is a major stakeholder in the construction works going on at KGL. Therefore, government engineers are always on hand to ensure that the equipment used in the works meet the requirements specified by the laws of Zambia.
Okay, so today we are here at Kafue Gorge Loyola, where there is ongoing construction of a new power station. One of the things that happens is that they receive heavy equipment which must be lifted and held as they are assembling the equipment that is used for power generation. But these equipment that they use to lift, the cranes, the forklifts, the hoists, are supposed to be certified according to the requirements of the Factories Act. So today we are here because they have completed the assembly of 2 overhead cranes, and both of them have a capacity of 200 tons. So we are here to ascertain whether it is true that these cranes are capable of handling a 200-ton crane. And handling means they can lift and hold in one position, but it also means they can lift and move in various dimensions. So that is what we have come to ascertain.
Every part of the crane, from the hook, the ropes, and every other component, is designed to handle a 200-ton weight. The government inspector's job is to verify the capacity of crane by subjecting it to a load test. To ascertain that the crane can actually lift such a weight, the inspector starts with checking the integrity of the mechanical structure and the operations. In the event that the integrity of the mechanical structure and the integrity of the operations do not meet the prescribed standards, they are brought to the attention of the contractors before the actual proof load test begins.
So we are going to do it in different stages. Because it is 200 ton, that is the rating, what we are going to do is to start at a lower capacity, below the rated capacity. So we are going to load it up to 75% of its rated capacity, which is 150 tons. So at that capacity, we will lift and hold and leave it there for a period of time, just to see how the crane will behave. Then after the 10 minutes have elapsed, then we are going to try moving it up further and down. There are motors that drive the hoisting motion. So we want to see if the motors are strong enough to provide the traction that is needed in this direction. And we'll do the same in the long travel and also in the cross travel. When we are satisfied at 75%, both for the static loading and the dynamic loading, then we are going to move to the rated capacity, which is 200 tons. Again, we will do the same. Something that is worth noting is that as we are doing that, the crane has those 2 girders, the beams. When they are subjected to a load, they have a tendency to deflect, to surge inwards like that. By design, there is an allowable deflection. So we are going to check the deflection at the rated capacity. and then compare it with the allowable deflection by design. And that will tell us whether the deflection is acceptable or not acceptable. So after we have done all these tests, it then remains for us to make the conclusion as to whether it has satisfied the requirements of the test and is ready for commissioning or not.
So this is a very huge milestone for the project, because at this stage there are some works that have been on hold for some time now, because we could not lower some components that we require for assembling the turbines. Now that the cranes are certified, we'll continue from where we are at now. Unit number 3 has the draft tube already done, the draft tube cone is done. So the next thing is now the assembly of the spiral casing. So unit number 3, 4, and 5 are at the same stage. So they are all awaiting the starting of the spiral casing assembly. So the major works from now on will be the installation of the spiral casing on unit number 2 completing, then number 3, 4, and 5 commencing the installation of the spiral casing. The overall completion of the project, the percentage now stands at 57% complete. So with the testing of the cranes, this also adds to the percentage completed. And then this will also mean we'll be able to now proceed with the other works. So we see the works progressing at a much faster rate going forward.
So once again, let us pay tribute to the Kafue Gorge Lower Hydropower Project. Its undeniable importance, its intricate construction, and its singular function to power the nation.